All right, so now let's talk about some special considerations that we need for our SN1 and SN2 reactions. The first being solvent. So let's look at how the choice of a solvent affects the rate of these SN1 and E1 reactions. And specifically, we're going to be talking about the rate of that first step, that rate limiting step, which is the formation of that carbocation. Okay. If we just want to take a look over here at at the relative rates of these reactions in these various solvents, we can see that the fastest rate is in water, our most polar solvent. And then we go decreasing as polarity decreases. And notice that there's a big jump when we go from our polar protic solvent to our polar aprotic solvent. So unlike what we saw for the SN2 reactions, an aprotic solvent actually has a slower reaction rate for these SN1 and E1. So why might that be? Well, let's remember, I guess let me take a step back real quick and also point out this dielectric constant business. So you may have heard about this in your physics course. A dielectric constant is a measure of how well a particular substance supports charge. Right, so it can stabilize charge. So water has a really high dielectric constant. All of our polar protic solvents, of varying degrees of varying polarity, have these high. And then when we go to our aprotic solvents, we're decreasing in our dielectric constant, right? And so this is what we had seen before when we were talking about SN2. These aprotic solvents are not as good at stabilizing charge. And when we were talking about SN2 reactions, remember that was a good thing in terms of the reaction progress. Like this is our polar protic solvent here, our normal reaction curve. And then if we took an aprotic solvent, that was even better for these reactions because it would destabilize the reactant, the nucleophile, which is the charged species in those reactions, right? So for SN2, aprotic solvents are good. For SN1, aprotic solvents are bad. So why would that be? Okay, it's because in this case, what is our charged species? It's the intermediate, that carbocation, right? So if we destabilize that carbocation intermediate by using an aprotic solvent, we're raising the energy of that intermediate. It's going to be harder to get there. There's a bigger jump in order to get there, right? Because again, aprotic solvents, they destabilize charge. When we were talking about SN2, that was a good thing because that destabilized our reactant. But when we're talking about SN1 and E1, that's bad because it's destabilizing that intermediate, making it harder to form that carbocation. Next consideration would be the actual substrate itself. What's that first step? The formation of a carbocation, the loss of that leaving group. So what's going to be more reactive towards SN1 and E1 are going to be alkyl halides that have the best leaving groups. So remember fluorine, we actually said even though it's an alkyl halide, it is the least, it's not a great leaving group, right? So that's going to be the least reactive for these SN1s. And then on the other hand, the other extreme would be the largest of the halogens, iodine, and that is the best leaving group. Remember, this also sort of has to do, I guess we could go the other way. This would be the worst base, and at this end is the best base, right? So this whole idea of being a leaving group corresponds to how good of a base it is as well. And we're simply restricting ourselves to the halogens. So the bottom line is an alkyl, an alkyl bromide is going to be better than an alkyl chloride, for example, right? So the best leaving group being the largest, and then it decreases from there. And then I guess just note, there's a large gap here, right? So we would still say, it's not that we're saying that an alkyl chloride doesn't undergo SN1 and E1 reactions. It's just if we have two of them that we're comparing, the iota will be faster. Okay, so now the substrate. So SN1 and E1 are only going to occur when you have these tertiary alkyl halides, which can form tertiary carbocations, right? it's all about the stability of that carbocation. Other sort of uniquely stable carbocations, sort of equivalent, would be a benzylic cation. Notice that the charge is not located on the benzene ring. It's kind of like one carbon removed. As well as an allylic carbocation. Both of these are resonance stabilized, which is why they form very readily, okay? The other thing that you got to watch, so all your SN1 E1s will occur because of a tertiary carbocation, benzylic carbocation, or allylic. This usually means a tertiary alkyl halide. The only thing you got to be careful of is if a tertiary carbocation can form through rearrangements, right? So if you have a particularly branched compound, something like this, for example, where the beta carbon is tertiary, in this case, you will see a hydride shift in order to produce that more stable carbocation. You can also have the same thing if it's what's called quaternary, or that carbon is bound to 4 other carbons. In this case, you'll see a methyl shift. The important thing being the carbocation that's formed is a tertiary carbocation, or benzylic or allylic, okay? That's the only ones that will undergo these E1 and SN1 type reactions. So a benzylic substrate, and just to hammer this home, right? If we looked at this carbon here, we would say, well, this is a secondary alkyl halide. But again, you just have to think in terms of the stability of that carbocation, what's going to happen. This bromine's going to, I guess we can show exactly. Right, we're gonna have this leaving group lost. And that is going to lead to a nice, stable benzylic carbocation. And so these will undergo these SN1 and E1 type reactions, just like a tertiary alkyl halide. So yeah, you know, the allylic, the benzylic, you got to watch out for. And then I think what's kind of the hardest to see are where there's going to be a rearrangement that's going to lead to a tertiary carbocation. Okay, so now next consideration, right? So talked about solvent, we talked about the substrate. Next consideration is this idea of stereoselectivity. What are the stereoisomers that are going to be produced? Good news, way easier than SN2 and E2, okay? So why is that? Well, let's remember what's going to happen here. The first step is that loss of a leaving group, so we're going to form this carbocation. Importantly, the carbocation is flat, right? It's in this trigonal planar shape, and it's got this empty p orbital that's doing the accepting of the electrons, right? That's what makes it electrophilic. Well, because of that, your nucleophile can attack from either direction, okay? So in this case, so in the case of, for example, SN1 reactions, you can get both the inverted, but also the retained configuration. Okay, so you're going to get a mixture because you're going to have nucleophilic attack from this side, but you can also have your nucleophilic attack from this side, right? So unlike the SN2 where we only saw the inverted product, here we are going to get a mixture of what we call a racemic mixture of both of these products. Okay, and just to hammer this home, if you actually like get down there and do the numbers, you'd see that actually the inverted configuration is slightly above 50%, meaning that the retained configuration is slightly less, okay? That's because you could imagine in the moments after that bromine pops off, it's still kind of hanging around right there, right? And so it's repelling the nucleophile from attacking that side. So you do have some preference for the backside attack, but it's roughly 50-50. And as far as this course is concerned, this is, to know that it's slightly more than 50, slightly less than 50, that's great. But what we really care about is these SN1 reactions produce racemic mixture, or a mixture of both R and S configurations, okay? So luckily not as big of a pain as it is with the SN2 reactions, especially the E2 reactions are a pain. So then when we go to the elimination product, again, we're going the whole shtick is that we go through that carbocation intermediate, which means that we don't have this sort of same consideration for the E2, where it was very specific as to how the hydrogen was going, how the hydrogen had to get positioned on the beta carbon to be lost. So you're always going to get a mixture of your elimination products, and then your only consideration is which one is more stable, right? Remember, we talked about the more stable alkenes, they're more highly substituted. So in this case, your major product would be this more highly substituted 1, 2, 3 versus just 1, 2 alkene. Okay, so for the SN1s, you're going to get this racemic mixture. For the E1s, it's always going to favor that more stable alkene. Same things, so that's the regioselectivity, right? Which constitutional isomer is favored. Same thing with the stereoselectivity, right? So if I have this particular compound here, I'm going to get a mixture of all my different products. What's going to be the major product? Well, these 1, 2, 3, 1, 2, 3, these are going to be the more stable alkenes because they're more highly substituted. But then in terms of stereochemistry, one of these is even more stable, and that's this first one here, because the large groups, I have my big bulky groups are on opposite sides from one another. So the ethyl group does not want to be next to the methyl group if possible, right? So as opposed to here, here are these two groups on either side. So this would be they are on Z-same side, so this is the Z conformation. The E conformation is going to be the one that's favored. This is, you can sort of broadly say that the E conformation is going to be more favored, but you got to be a little bit careful. So because, so for example, if we had, let's say a fluorine there, and then this was this big bulky tert-butyl group, well, this is going to win in terms of priority. This is going to win in terms of priority. So this is the E conformation. However, what really matters in terms of stability are our big bulky groups next to one another, right? So here, this tert-butyl group next to this ethyl group is going to be less favorable than having the fluorine next to the ethyl group. So I don't want to, you can't really commit. It's not as easy as saying it's always going to be the E product that's favored. So just be careful. Okay.